Hi team, we're going to talk a little bit about some statistics that we're going to use to analyze some of our data here. The first thing I want to remind you of is there's a couple different types of data, and a classic one is continuous data. This is something that could be, you could have the value of 1.2, 1.8, 2.0, 12.71. Continuous data can have almost any value. And that's what we're going to be working with for the most part in our class. There are other types of data, of course, that might be more correctly termed discrete data. And discrete data can have categories. It can be nominal or ranked. So an example of a categorical or a nominal data might be course 1 versus course 4. Even if you're just including 1 and 4, course 4 isn't 4 times better than course 1. This is just the title of it. We could call it course Larry and course Steve. Another example of discrete data would be ranked data, like first place, second place, third place, fourth place, where these actually mean like placements or rankings. But for our class, we're going to be focusing on continuous data. So let's talk a little bit more about how to work with that. One of the first things we want to be able to do is to display and summarize our results. And often that is done using the mean or the average of the sample plus or minus the standard deviation. And some people prefer to use the standard error. For our class, either one of these will be just fine. The standard error is the same thing as the standard deviation divided by the square root of the number of things you're sampling. But as long as you are clear about which one you're using, either one of these is fine for our class. To simplify, I'm just going to include standard deviation here. Let's draw a graph that shows some data on it. And on our y-axis, this is what we're measuring, of course. This is our dependent variable. And on our x-axis, this is our categories of data. So our categorical variable is down here. This is one of the things that we're changing. And our x-axis is going to have our continuous measurements. The categories we might care about in this class are wild type plants versus mutant plants. Or maybe we care about, let's care about cow versus fish. So we've got two categories of data and we're going to measure in both of those categories. So I'm going to draw a bar chart here. And from the way this is shown, it appears that the means of both of those categories are the same. So including the means in your data analysis, super important. But it's also really important to include your standard deviation. Because if we had data that looked like this for the cows, and maybe data that looked like this for the fish, you can imagine that the standard deviations here would look very different. That is, the standard deviation or the spread around the mean really tells us something that the mean doesn't. It tells us sort of how accurate or concise the data that we're measuring is, how spread out it is. And if we want to call things statistically different, it might be nice to have really tightly clustering values around the mean. And by the same token, having very spread out values can tell us something about what's happening in the population as well. Now, if we're going to compare only cow and fish, it's reasonable to use a t-test. This t-test will give us a p-value. A p-value that's less than 0.05 usually means that the two things we're measuring are significantly different. And a p-value greater than 0.5 is going to indicate, p greater than 0.5 is going to indicate that there's normal like noise in the data. So the significantly different means there's probably something biologically meaningful going on. P greater than 0.5, we usually say this is not biologically meaningful. That's an overgeneralization. When we make the data just a little bit more complex here, let's add in a third category. I'm going to call this third category honeybee. And we've got a bunch of data in this category as well. In order to compare three different things, we're going to have to use an Anova test. And Anova, again, will give us a p-value. And that p-value we can interpret in just the same way. Again, we're looking for something less than 0.05. But all an Anova p-value tells us is one of these groups is different. In order to know which groups are different from one another, and we've got three in this case, we need to do a post hoc test or a secondary test, and I like to use Tukey's HSD. And this Tukey's HSD lets us compare each of the groups, the means of each of the groups. So let's talk just for a second about what Tukey tests actually look like. For example, we could take the cow mean minus the fish mean and ask, is it equal to 0? If it is, if cow mean minus fish mean is pretty much equal to 0, that means there's no significant difference. We're going to get a p-value greater than 0.05. If we find that the cow mean subtracted by the fish mean is not equal to 0, that means there is a significant difference. P-value is less than 0.05. And of course, in a post hoc Tukey test, we're going to not just compare cow and fish, we're going to compare cow versus honeybee. We're going to compare honeybee versus fish, and we're also going to compare cow versus fish. So the Tukey test will let us know from the Anova which one or more than one of these groups is actually different. So in summary, when you're doing your data analysis and your data reporting, you want to include the mean plus or minus the standard deviation of your data, as well as a statistical test to let your reader know how different the means and standard deviations of your different categories might be. I'm happy to talk more about this in class or in lab, so please bring questions.